Okay, we are good. We are good. Good morning, everyone, and welcome to Global Flood Course Cutting Initiative. Today, we are truly honored to have Professor Hamid Moradkhani from the University of Alabama as our keynote speaker. His significant contribution to our field make him exceptionally well in our field, so he doesn't need me to introduce him. And it is a privilege to have him with us today. Before uh, Professor Moradkhani start his presentation, I want to give you all a brief kind of update about this initiative. So this initiative is started by GEWEX, Global Hydrology Panel, um, around 2 years ago. And then we had a workshop, an online workshop, and then we wrote kind of a white paper and then write a proposal submitted to the GHP panel, and we got approved. And we started this bi-monthly meeting, and then we invite keynote speaker across the board to provide the insight, the kind of outcome of the funded project in order for us to synthesize the result across the globe and then write a final report to GEWEX. So if you guys work on flood-related research, I would encourage you to add your publication in the Google Doc that I provided in the chat. Please go through the document and add your thought, add your publications to the report so that we would be able to use those information you provided in our final report. Or we have this monthly meeting every the first Friday of every month at 9 a.m. Eastern US time. And we have actually very kind of great invited speaker. Here you can see a list of them. Let me find the link for you guys. Our previous speaker as well as the upcoming speakers. You can go through this link and see if your schedule allows. We would be happy to have you in our next kind of presentations and or meeting. And again, thank you for showing up. And I'll let Professor Moradkhani to start his presentation. Hamid, are you ready? I believe you can share directly. Great. Can you see if you can share?
Yes, of course. Let me just those few things. Okay, I guess it should be this one. Do you see my screen?
Yes. Good.
Wonderful. Great. Thank you, Vidya, for the nice introduction. I appreciate that and the opportunity to present today. Nima asked me a while ago to provide the title, but I didn't know what I was going to talk about. So I told him it's going to be about predictability, prediction, vulnerability, and risk, all those things. So I chose this title for my presentation today, and causative mechanisms to predictability and prediction of hazards for disaster management. I would like to start with this figure that is showing 2 decades of flash flood events that we visualize for each month at the county scale based on a storm event database of the National Weather Service. And as you see, the total flash flood events that we analyzed was nearly 75,000, and nearly 40% of those events caused property damage over the 20-year time frame, and with mean duration of 4 hours and total fatalities of 64 per year and injuries of nearly 300 per year. Then we published actually that paper In this journal that I'm just showing, and this is also showing the frequency of a few variables associated with floods and some of the lessons learned. For example, we see that the state of Texas indicates the highest value in terms of number of events, injuries, and fatalities. And two hotspots of flash flooding in terms of injuries and fatalities are Arizona and Central Texas, as you see. And generally, East Coast seem to be more hazardous for flash flooding than West Coast. And Hurricane Harvey caused the highest property damage a few years ago with abundant mortality, as is shown here in the red box on the right. And as you see in this green box, it's showing 2012, that was the least number of flash flood, and that was because of the significant drought we experienced in the US. And that's why you see that changed the trend a little bit. And then now the question is how we can enhance the Earth system predictability to protect the livelihood and property damages. Basically, on the shorter time scales, we think of phenomena such as tornadoes, flooding, storm surge, or wildfires, and then moving to the weeks and months time scale of heat and cold waves, and droughts and flood. And as we go even further in time, looking at sea ice, land ice, sea level, and global temperature changes, that we are not dealing with those today. I'm mostly focusing on flood. So essentially, the enhancing understanding and enhancing the predictability of flooding was considered two perspectives. One is the atmospheric perspective that we call it meteorological predictability, and that emphasizes synoptic scale atmospheric circulation patterns and the predictability of the precipitation input itself. And the second actually perspective or consideration is the watershed perspective, where it focuses on the state of catchment, including land cover, slope, aspect, morphology, and initial conditions, and the nature of precipitation input to drive an understanding of causal mechanisms related to flooding. So the main question we are after to answer is how well we can estimate the amount of water stored in the snow and soil, and that depends on the fidelity of the hydrologic model simulation and effectiveness of the data assimilation that we use, and I will explain briefly about those as well. A few years ago, we conducted a study to look into the natural causes of floods, and based on the studies at the watershed scale, the proximate natural causes of hydrologic floods can be classified as single-day rainfall that rapidly exceeds infiltration capacity, and multi-day to week-long rainfall that exceeds soil moisture holding capacity, and several day rainfall that result in a combination of mechanisms associated with single and multi-day rainfall, etc. So given the extensive damages caused by extreme floods, it's very important to develop a unified understanding of the natural causes of extreme floods at near continental scale. And in particular, we focus on the atmospheric circulation patterns leading to heavy rainfall, which can be especially used to inform continental scale modeling and forecasting efforts. So in our work, we used self-organizing map, a simple artificial neural network that many of you are familiar with, is unsupervised procedure to do the clustering of climate reanalysis data to identify synoptic scale atmospheric circulation patterns associated with extreme floods across the continental US. Then we assessed the flood characteristics, including frequency, spatial domain, or event size, seasonality, etc. So on the left, you see the annual frequency of flood occurrence. We expressed it as percent of gauges associated with that pattern relative to all reporting gauges at the time of flood. And on the right here, you see the most prominent pattern for each grid cell. Basically, dots indicate at least 50% of peak over threshold floods were caused by that pattern. So we published that paper in Nature Scientific Report in 2019 with my postdoc, Catherine, who's a faculty right now. And now that I discussed the causative mechanisms associated with flood, let me talk about the tropical cyclones as the most devastating natural disaster and how we can communicate their hazards effectively. Here I'm showing the track of 17 costliest tropical cyclones and their corresponding precipitation magnitudes. The current TC or tropical cyclone that this TC hazard characterization framework lack systematic consideration of compounding effects of hazards, such that the scaling system relies only on wind speed. So that's what the Saffir-Simpson scaling is. However, we saw that certain hurricanes like Hurricane Katrina in 2005, which falls under category 3 based on Saffir-Simpson scaling, has been the costliest tropical cyclone on record. So we know that the wind forcing accompanied with extensive pluvial coastal flooding is not reflected in the Saffir-Simpson indexing. So we thought, okay, let's develop a bivariate hazard characterization approach that brings wind and precipitation together. And on the left, actually, you're seeing upper left, you see the schematic of the category, considering only wind speed, what's happening in Saffir-Simpson scaling. And subplot on lower left is our hypothetical categorization, considering both wind speed and precipitation, basically a joint probability between these two. And then we develop, we use the cupola functions, bivariate cupola functions to develop these, and the colors and symbols are representing the categories for tropical cyclones based on Saffir-Simpson scaling and the bivariate distribution. So each curve here is showing a contour lines having the same exceedance probability to the wind speed threshold, and based on Saffir-Simpson scaling, and the label over each curve is the multi-hazard hurricane index. We call it MHI. And we published this in 2020 in Environmental Research Letter with my former postdoc, who's a faculty in Korea right now. And then we extended this work. We said, okay, let's bring another main driver into this, which is the storm surge. In previous work, we just considered wind speed and precipitation. In this work, we have three variables, which is wind speed, precipitation, and storm surge. And we implemented thorough statistical analysis of hazard variables using wine cupola to characterize the mutual correlation structure, and estimated the non-exceedance joint probabilities associated with this. And what you see on the left here, the middle plot, this one, it shows the joint cumulative distribution of wind speed, rainfall severity, and surge, with blue color representing lower non-exceedance probabilities and red showing higher values. And the plot on top right shows the distribution of tropical cyclones based on multivariate hazard index. And in lower right here, I'm showing some of the most devastating tropical cyclones in the US history that were associated with relatively low wind speed. However, they cause significant damage. So this is some result and showing the track of 102 tropical cyclones that made landfall in the US, Atlantic and Gulf Coast between 79 and I think 2020. And the circles you see show the location of 36 costliest tropical cyclones. And on the right, I'm showing the comparison of damage ranks using both univariate and multivariate. hazard index. For example, subplot A that I just bracketed with this dashed line is the adjusted damage of 36 costliest tropical cyclones, and we rank them. And subplot B and C on the right is just estimated products of hazard and vulnerability, basically a risk. And overall, while Saffin-Simpson scaling has a good correlation with this reported damage, which is 0.59, I mean, the middle plot, we see that if we bring the storm surge into play, we get much better correlation of what we have estimated using our multivariate index with what happened in reality, which is the damage here. So we could rank the hurricanes and the severity and the hazard of these hurricanes much better, from 59% to 78% correlation. So we are hoping that the National Hurricane Center one day adopts such approaches, and they see the value of bringing other drivers into this hazard characterization. So since we were talking about tropical cyclones and extremes, etc., I thought, okay, we need to, I'm going to shift into modeling. We thought, okay, let's see the impact of forcing data on our modeling, hurricane-induced flood modeling. And we know that forcing data plays a big role and is the most erroneous component of the hydrologic cycle. So numerous procedures have developed techniques to merge precipitation estimation from different sources to improve the accuracy of quantitative precipitation estimation. However, these attempts are mainly focused on spatial and or temporal correlations between various remote sensing sources. So we thought, okay, let's combine the skill of different products and get a combined product using a deep learning approach that can simultaneously downscale and merge multiple user-defined precipitation product. And we verify or validate them with rain gauge observation as target variable. So we use all these products, as you see, and they come at different time and spatial resolution. So we needed to unify this using a deep learning approach, which is convolutional neural network that we developed a few years ago. We published in 23 in remote sensing of environment. So basically, that procedure combines multiple layers of three-dimensional convolutional neural network and convolutional LSTM to fully exploit the spatial and temporal patterns of precipitation. And the figure you see on the left is just showing a schematic of data processing and too much computational complexity we experience. And to appreciate the computational complexity that I'm just referring to, I should mention that all data sets were downscaled to 0.05 degrees spatial resolution. And then the images of all 7 products, satellite and reanalysis product, are then concatenated over time to produce 3D images for each product. So considering that we had 1,000 stations chosen for this study, 18 years of data, and 7 products, I think we had nearly 46 million clipping operations that needed to prepare the entire training data set for us. So we used computational resources that I have in the center I've been directing, so multiple GPUs, etc. So we could parallelize the system on this, and we trained and we developed the data set. This is just showing the testing, training, and validation. We basically used 12,000 stations over the CONUS. I think, yeah, 12,000 total we use for this purpose. And this is just showing the comparison of our product on the top left, bracketed here. That's the precipitation data fusion network that you see is a combination of all these products. And we see that the scale is, in terms of Killing-Gupta efficiency, is better than any individual product that we have here. So we provided the codes and everything on the GitHub and the data on Zenodo. And also recently we developed the visualization of this data. So I would like to just demonstrate briefly on another screen I have here. So here we have everything available at daily or aggregated product. Basically, if I choose, for example, daily, and I choose any day in the whatever you like to choose, let's say, okay, I don't know, March 12th. So this is the product that you see immediately, and you can even develop or access the aggregated product for certain range, calculate the average, maximum, minimum, etc. You can draw a polygon, and you just put the polygon here. And for this polygon that I'm choosing, it just focuses, and you can just download that specific data um, within that polygon. Or it could be any shape that you can upload the boundary wherever you are interested in. You just put it in, or you can enter the location, custom shape. You can say go to that county, etc. And it gives you all the information. You can zoom in and you get all these values very closely. You have a dynamic and static view, and all kinds of possibilities is there that you can access the data and use for any hydrologic modeling. I invite you all to take a look at my website, and is there for you to use. So I think I'm gonna go back to my presentation. We are doing this precipitation data fusion because we need it in our modeling. Can we trust on a single data product? No, that's why we combine several precipitation products to get combine the best product that we can use in our modeling for simulation and forecasting. So we do that, for example, in case of hurricane-induced flood modeling with hyper-resolution modeling, and that I would like to talk briefly. This is from a study that we conducted, actually performed a few years ago. The objective for our study was synergistically assimilate soil moisture, satellite soil moisture data at fine spatial resolution, and also stream flow observation into a WRF hydrologic model that is currently called National Weather Model using National Weather Center here at the University of Alabama. So we aim to understand the extent such development can contribute to reducing uncertainties with a special distribution of soil moisture at finer scale. The data set that we also developed, the 1 kilometer downscale SMAP soil moisture product that we developed 6-7 years ago, and we published, and is extensively used for local application. And we assimilated that product with streamflow all together using this evolutionary particle filter data assimilation technique that we developed a few years ago to estimate the flood condition during hurricane, like Hurricane Harvey. For those of you who are not familiar with the data assimilation, I just provide a very brief definition of what it is. So data assimilation, in principle, merges observations and model predictions just to infer the system state and parameters. And we have a variety of techniques and in literature, like direct insertion, Newtonian nudging, to more sophisticated Kalman filtering, ensemble Kalman filter, and particle filter, etc. And but in order to understand how it works, it's just that you have the hydrologic model, like here's land surface model, soil, vegetation, atmospheric transfer scheme. You just drive the model to the next time step. You get the model forecast when the observation from satellite, from aircraft, or any institute data becomes available. You assimilate that data into the model to correct the model states and parameters. Then after updating those quantities in the model, you drive the model to the next time step and you make the model forecast again. So this is a sequential process, and we call it ensemble and sequential data assimilation. And the application of that is just during the Hurricane Harvey, and this is just showing a graphic. If you look at the river network, that when it approaches the hurricane, you see a darker map, the river network, how the flood is propagated through the river network. And we published this in 2020, but we extended the work just recently to 3 other basins: Savannah, Mobile Basin in Alabama, and Galveston again in Texas, just to see the impact of doing data assimilation to characterize the peak flow better. And by the way, so we chose this basin because each has experienced hurricanes in different time. We wanted to test them to see if data assimilation is effective during the peak flow condition when a hurricane happens. So this is some result stream flow forecast by data assimilation during peak flow. And what you see here is just the prior and posterior distribution, full characterization of uncertainty for each one of these points, blue dots that you see, the stream flow forecast across the study domain like Galveston in Texas. And we see that after data assimilation, the probability distribution is much closer to the observation, which is showing the more accurate analysis and forecast for us. We published this in HES last year. And then I would like to touch on compound flooding a little bit, given the time we have. This is from a paper that we were invited to publish actually in Reviews of Geophysics about the compound flooding, not only compound flooding, but looking at the advances and frontiers in riverine and coastal flooding, and compound flooding was part of that. And many of you know already what compound flood means. Compound floods occur when multiple flood drivers combine to amplify the overall flood impact. So these drivers can include riverine flooding, coastal flooding, urban flooding, or even infrastructure failure. So the combination of these could result in compound flooding. So this is showing the schematic that we developed for that review paper about flood generating processes and key factors that generate specifically riverine or fluvial flooding and inundation areas. And we provided different perspective how we approach the problem from watershed perspective or from hydrodynamic perspective. What are the important drivers or components to consider in the modeling? But it comes to another or set of drivers, which are the coastal flooding. And according to literature, nearly 40% of the United States population live in a county directly connected to a shoreline. And according to NOAA, nearly half of the United States economy output is increasingly threatened by coastal flooding. So to help these vulnerable communities prepare against escalating flood hazards driven by oceanic and atmospheric processes at the coast, a thorough analysis of extreme water level dynamics under various forcing scenarios are essential. I should mention that 1 billion of world's population currently dwells on land less than 10 meters above the high tide line. So this speaks the volume and the importance of looking at compound flooding more closely. This is generally showing the full representation of coastal compound flooding that requires a model that accounts for wave generation, storm surge, and tide processes in the offshore boundary, and short and long wave and shoaling and all of these that need to be considered. We explained those in detail in the paper we published again a year and a half ago about nature-based solution as buffer against coastal compound flooding. And we discussed the holistic process-based modeling framework that demand the integration of various numerical models, including ecological, hydrological, hydraulic, and ocean circulation or hydrodynamic models. Then it's about the coupling, how we develop the coupled model for compound flood modeling. This is an idea we developed a few years ago how we can, from the tropical cyclone, and then you can consider two sides, low pressure wind and low pressure moisture that result in storm surge and extreme rainfall, and the processes involved, and it comes to land surface in the middle. But when we look at the flooding on the land surface, that flooding is driven by upstream boundary condition and downstream boundary condition. Upstream can be actually it's part of the inland flooding that we thought, okay, maybe we can use data assimilation to characterize that boundary condition. And for downstream, we can do the same, but we have ocean circulation model. But again, the data assimilation can be used to characterize the boundary condition better to develop this compound flooding. And this is a perspective paper on uncertainty quantification in compound flooding that we were invited in 22. We published in iScience. We elaborated in detail about the framework for uncertainty quantification in compound flooding. And we elaborated on cascading uncertainty that is resulting in the interplay of hydrologic, hydrodynamic, and oceanic models in compound flood modeling and forecasting. So this shows how in different layers of modeling you can use data assimilation as a versatile and very complete framework to characterize the uncertainty in compound flood modeling. So I invite you to take a look at that paper if you're interested how to approach the uncertain quantification in compound flood modeling. And then one application of data assimilation in compound flood hazard assessment. In a paper that we developed and published, we showed an application of data assimilation to quantify and reduce the uncertainties in flood hazard assessment. Our domain of interest was again Galveston Bay in Texas during Hurricane Harvey and Delaware Bay during Hurricane Sandy. So we consider these two as case studies. And then, then the data assimilation algorithm itself, the ensemble Kalman filter that we used, and considering that the ensemble Kalman filter is prone to mass and force balance violation that many people do not acknowledge, or they just simply ignore that. So given the specific formulation it has, we use an approach which we elaborated in the article, how we deal with the mass and force balance closure. And then we took care of this data assimilation properly. I should mention that the time series of observed hourly water level that are obtained from NOAA tide and current portal that we elaborated in detail in the paper, and how we use the data assimilation actually to characterize the compound flood hazard. So toward the end, I would like to go briefly and very quickly on using the vulnerability concept and risk concept, how we bring that into this and the data set and very detailed fine resolution data set we developed. We started these kinds of studies from 2019, 2020, although numerous studies have estimated different aspects of vulnerability to more visually damaging hazards in the US, like the tornadoes, hurricanes, and floods. There is not yet any comprehensive assessment of flood vulnerability across the continental US. So vulnerability, what is vulnerability? Is the result of a combination of different parameters reflecting the system's susceptibility to harm and ability to cope with hazards, which is a function of its exposure, as I'm showing here, sensitivity and adaptive capacity. So on exposure, we mean, for example, the frequency of flood, the state's population, and on the sensitivity, I mean states' likelihood of being negatively impacted by flood, taking into industries like agriculture, water recreation, and hydropower into account. And finally, adaptive capacity, which is the state's preparedness for flood and ability to recover. So by combining these three components, we can get to the vulnerability assessment. Then we looked at all these socioeconomic variables or information to develop this vulnerability assessment, and how we can use a combination of this socioeconomic information and hazard that I'm going to show quickly right here. This is showing a two-way cross tabulation on map to map the coincidence of socioeconomic vulnerability index and also the flash flood hazard characteristics. By those flash flood characteristics, I mean the duration, frequency, and magnitude and severity. So we basically overlay these flood characteristics over the socioeconomic vulnerability map that we developed to come up with this hot spot, cold spot areas across the continental US. But this study is conducted at county scale. So the resolution is the county scale. We published this in Nature again in 2020, but that was the motivation for us to go after much finer resolution, which is this. So we developed a socioeconomic and infrastructure vulnerability. So we brought the infrastructure into the framework at block level. So this is how we collected the information: demographic, infrastructure information, socioeconomic, and building stock, essential facilities, and all detailed information that you see on the right. We brought all these components together, and we developed a machine learning framework to put all this data together again. And this is the block level vulnerability assessment that we developed across the continental US. We published in Nature Communication in 23, and it has all detailed information about the socioeconomic and infrastructure vulnerability. These are just few examples of different cities and states that you see the vulnerability map. We had this in the paper we published, but I thought, okay, let me just develop the whole visualization, and here it is. I hope you see this again. This is the vulnerability map that we developed across the continental US. As you see, you can hover around the US, and at any point where you see my cursor, you can see the vulnerability index in different categories from very low to high value, not only at state level, but you just click and zoom in, then it goes to county scale. As you see, you zoom in further and it goes to the census tract. This is the census tract resolution. Again, different vulnerability index, and you just click in, go further and further. Then it goes to the block level, which is the finest resolution possible to estimate the vulnerability across the continental US. So you have all this information. Wherever you go, you have the vulnerability index, you know what is happening. And just wanted to mention that we are now working on an LLM that I'm not reporting here. I'm just mentioning that an agent that it actually capture all this information, and it tells you, okay, where you can build something or if it is safe, etc., based on this information and some risk analysis that we conducted. So I guess I'm going to close this and go back to the presentation. Last thing I just wanted to mention is the use of social media analytics for disaster management. And this was motivated a few years ago that I had a student from computer science working with me, still working with me as a senior scientist and AI software engineer. We thought, okay, let's use a comprehensive analysis, do the comprehensive analysis of Twitter data for disaster management. And we know that the use of social media platform like Twitter and now X significantly increases during natural disasters. With the emergence of several social media platforms over the past decade, many studies have investigated the application of these platforms. So these are the motivation why we are using social media data analytics for this. And the methods that we use was based on the natural language processing, which is a branch of computer science, as you all know, a type of artificial intelligence. we do the text pre-processing, then text classification, then sentiment analysis. All of these that we elaborated in detail in our 22 paper that I'm just showing here. The title of the paper we published in Sustainable Cities and Societies. This is over the Texas and the hazard risk awareness index that we developed that considers multiple factors, including the number of tweets, population, rate of internet use, or characteristics of the natural hazard per geographic location. So as I mentioned, we use natural language processing, and we analyze, I think for that paper, we analyzed over 18 million tweets during Hurricane Harvey, and that enabled us to subdivide the tweet contents into several categories to do further analysis. And we developed this technique that you see, hazard risk awareness, a technique that we developed that combines the hazard and the relative number of tweets that we had. So you see more detail. This paper is well cited, and that motivated us to use NLP in few other studies. We even in one study we used it for seeing how climate polarization is looked at, given the political parties we have in the United States, how Republicans versus Democrats see the impact of climate change on hazard. We published that paper again, and some other paper using another one using NLP for even fire characterization over California. So we found it very useful tool. But I think I'm going to stop here in the interest of time, and thank you so much for the opportunity. I get any question.
Great. Wonderful, wonderful talk. That was huge. Wow. Excellent. Any
Right.
question for Professor Moradkhani? He provided a lot of information. You guys, if you are a graduate student or postdoc, I hope you could take advantage of all those knowledge. I mean, it's amazing, and we are blessed to have him in our community. It just realize that this type of work needs a lot of effort, a lot of energy, weekend works, after hours work, and you are freely getting this knowledge now. So if you have any question, please raise your hand and unmute yourself. I saw two, three hands. Some of them did drop quickly. I mean, yes, Bernard, thank you for your continued support. Yes, you go ahead, please unmute yourself and ask your question. Can you hear me?
Thank you,
Yes.
Prof, for the wonderful presentation. I'm sorry I joined late, but I must say I really enjoyed the last half of the presentation. Very exciting. So recently, Nairobi, Kenya faced a lot of flooding. The impact is still being witnessed 3 weeks after the flood. I was contacted recently to help in analyzing the citywide flood risk for the whole county, and I'm just wondering, we are in data scarce region. How will the Prof recommend ways of perhaps using, consolidating data or coming up with this kind of information to inform the policymakers in data scarce regions, especially for the social vulnerability aspect? Thank you.
Well, great question. Thank you, Bernard. So yeah, great question. Data scarcity has always been a big challenge. So the notion of on-gauge basin analysis has always been there for hydrologists. That's kind of similar to data scarce region where we don't have much of a data. And to me, the only thing that comes to my mind is the use of satellite data that is widely available, but they come at some inaccuracy that we cannot do much about it, but the combination of these products actually provide something for us that is useful, like that combined precipitation product that we use. We combine multiple satellite data and we downscale them to a finer resolution. I think satellite data is the way to go, at least for data scarce region. But data is everything. I think we should think about how we can install gauges and how we have a concerted effort to collect more data for modeling. If you don't have the data, we cannot do much. That's what it is. And well, we can use artificial intelligence, but artificial intelligence rely on data itself to be trained. But I think some sort of regionalization and borrowing information from those areas who are heavily gauged or they are not data scarce, maybe we can transfer knowledge from those basins and those countries, those regions to data scarce region. That's the only thing that can be done at this point.
Great.
Yeah, thanks very much for that. I really appreciate.
Sure.
Yeah.
Great.
Could this work be also shared just to kind of follow the methodology if one is interested to replicate this kind of work elsewhere?
So what was the question exactly? You want to use the...
I mean, if this presentation can be shared for, a later follow-up, and if I need to replicate some of these approaches.
Yeah, all of these have been published, and the video has already recorded this, so I leave it to her to see how the protocol is. But we published all of this, and all the actually papers are on my website. You're welcome to go to my website, the data products. We have a variety of things there. You're welcome.
Cool. Thank you very much. Yeah.
My pleasure.
Yeah. Great. Birna, thank you. Any other question you guys may have? So I have a quick question, Hamid. I was wondering how you guys calculate the uncertainty for compound event. Is it a little bit, I know, tricky?
Compound event, let's see.
Yeah, you show a kind of
I show
graph.
the framework.
Yeah.
This framework. So we provided this perspective how you can characterize the uncertainty. So basically here, I don't know if you, let me see. Actually, I don't know if it got stuck. That's very interesting. Do you see that?
Yes.
All right. So this is the perspective on uncertain quantification. Basically, what you see here is that you have different layers to approach the compound flooding. Okay. So one layer is about the hydrologic modeling. The other layer is the hydrodynamic modeling portion. And the last layer is ocean circulation modeling on the right. So each one has its own uncertainty. Hydrologic model uncertainty, model structural uncertainty, parameter uncertainty, forcing data uncertainty, initial condition. So each of these uncertainties on each modeling chain actually can be characterized by data assimilation itself. So you do the data assimilation, characterize the uncertainty, that information from hydrologic modeling is going to the hydrodynamic modeling, but with full characterization of uncertainty. Then that uncertainty is propagated into hydrodynamic modeling. You do another data assimilation, assimilate flood, for example, water level observation from variety of sources, like SWOT data. You just assimilate those to better characterize the uncertainty of hydrodynamic modeling. Then that goes to ocean circulation modeling. You do the same data assimilation technique for characterizing the uncertainty of ocean circulation. So the overarching goal is to use data assimilation framework, which is the most comprehensive framework for characterizing the uncertainty. To my knowledge, there is no other technique out there to quantify the uncertainty more comprehensively, because in data assimilation, you can characterize forcing data uncertainty, parameter uncertainty, model initial condition uncertainty, and model structural uncertainty. That's the only framework that I know that brings all these uncertainty sources together. So I welcome you to take a look at the paper.
Yeah,
And even this paper, it goes quickly. Sorry about that. This one. So I highly suggest that you take a look at the reviews of geophysics. We elaborated a lot on how we also characterize the uncertainty there.
Great. That's really nice.
Sure.
That's very good. I was wondering if, I mean, I went and I remember data assimilation, first thing you've done, right? So I was thinking whether data assimilation could be coupled with the AI system as well, or you have done before.
Yeah, we have done it. Actually, I didn't talk about that. We have done it. We published a paper on generative data assimilation. We use generative models, and we conducted data assimilation within that framework. I had actually the slide, but I removed it because there was too much to talk. So I had to remove a bunch of the slides from my collection. Then, yeah, we have done it, and we are doing two others, actually combination of data assimilation and AI that we are gonna publish them soon, hopefully.
Yeah, nice. Very good. I really enjoyed it. Very nice.
Yeah.
Yep.
Of course.
Thank you very much, Hamid-jan. It was really wonderful to have you here. Thank you all for joining us. And again, I want to mention that our next speaker for May 1st is Professor Hayley Fowler from Newcastle University in the UK. So if time permits, please join her presentation and bring your wonderful question too. So thank you again all for joining us today, and thank you, Hamid, again for your wonderful presentation. We did enjoy it a lot, and I wish you all a great weekend. Thank you.
Have a great weekend too. Bye-bye. Bye-bye.